Good afternoon. This is CIVE632, Computational Hydraulics and Hydrology. And this is the second class of the 11th week. And the subject today is the last lecture on the chapter or section on roll waves. We are going to review a paper, or actually a couple of papers that I have done in the last couple of years. Let me, first of all, let me say that a couple of years, I have contacts in Bolivia for a long time. Friends out there in both La Paz and Cochabamba. And I got word in the early months of the year 2019 that they were having an unusual succession of these roll wave events. I believe in the year 2019, I'm not quite sure of the number, but I know that there were a lot. There were more than usual, like 10 or 12 per year. That's a lot. In both of these channels, the Achumani and the Huayna Yahuira, which are the ones that usually have these roll waves, or these pulsating events, or pulsating waves as they call them out there. So what I'm going to do, well, what happened was that I decided to go out there, so I headed into La Paz in May of the year 2019. And then I also went back in September, I believe. They invited me for some other issue. So I was, in the year 2019, I was twice in both La Paz and Cochabamba, gathering data, meeting with the people. I gave a lecture actually out there in La Paz on the first visit. And that led to in the month of June, right after coming back from La Paz, I released an extensive report. I sat down to write a report. It took a while, but I was interested in doing this, and we finished it up in June. This report is that I'm going to review today is dated June 2019. And then the second report, or the second article, dates to, I believe, January of the year 2020. And I'm going to talk about that later. First, let me talk about the first report. So what I'm going to do today is I'm going to share the screen with you. Okay, do you guys see the green page?
Yes, we can.
Okay, cool. So again, I do repeat. I wrote this report in June 2019, right after coming back from La Paz, where I had documented, met with the people over there, and visited the sites, both channelized rivers that I'm going to be talking about today. So what I intend to do today in the next 40 minutes, I'm going to read with you and explain what the content of this report is. It's a very extensive report, probably about 30 pages. So I obviously am not going to be able to cover it all in detail. So I'll use maybe 40 minutes. No, not 40 minutes. Yeah, 45 minutes. And then the second report, which is a little shorter, will be the second part of this class. Now, I do want to say that I have worked up a problem for you to do, and that will require that you understand the theory, which is this first report, and then you understand the practice, which is the second report. Once you read this report or this paper, and then you go into the second paper and redo or reproduce what I did, which is very explicitly stated in there, that you should be able to do the homework. Otherwise, you won't be able to. Simply put, you won't be able to, because it's a tough subject. It's a thick subject. Okay, so let me get started here with the first report, and this is called the control of roll waves in channelized rivers. As you know, even Montuori, that wrote his paper, the one that we briefly looked at, last class, he was talking about controlling the roll waves. The control of roll waves, based on what we know from the experiences in La Paz, is absolutely necessary. Unfortunately, the La Paz channels were built 30 years ago, at least 30 years ago, because they needed to develop the land and channelize the rivers. As you can see in that figure in there, they've got the channel. This is, I believe, to be honest with you, I think this is the Achumani, but I'm not sure. There's both of them are very much the same. They have the same design, the same the neighborhood and so forth. Not the same neighborhood, but they're kind of parallel to each other. They're two rivers that are parallel to each other. So as you can see, there's buildings in the back. They developed that area. They felt, I believe, at least 30 years ago that it was necessary. They channelize it, and they made the mistake of putting the rectangular channels. As you know, not most, but I would say it's very typical to do a rectangular channel design in open channel hydraulics. But that's for channels that are regular, they have regular slopes. A slope that does not go above supercritical would be less than 1%. Less than 1%. It's been demonstrated under normal conditions, 0.4% will be around critical. That can be calculated with our formula. So 1% is already supercritical, but it's not yet unstable. For the slope to get to be unstable, it had to be 2, 3, 4, 5%. Now these two channels have 5.6%, so more than 5, less than 6. So these two channels were going to develop roll waves if allowed to. But at the time, this is 1960s, 1970s, the people out there didn't think about it, so they just designed the rectangular channels. Our proposition is that they should fix these channels. How? How would you fix a channel short of redoing it completely? Which I don't think they're gonna do. For some reason, it's just not in the cards that they're going to come out and say, "Oh well, let's redo this thing from the beginning." They may have to modify. They may have to change it. To be honest with you, I have not heard that they've started doing this. They're thinking about it, like usually. Uh, to do such a project requires not only the engineers, it also requires the politicians to decide to do it. It's a large project, it's very costly. Funds will have to be identified to fix this problem, but it is a problem. Um, I was just on the phone 15 minutes ago with Beatriz Choque, who is my co author here. And Beatriz said that the unfortunate, she no longer works for the agency, but she has heard that there's been a few. Apparently, in the year 2019, there were a lot, and it has kind of receded, and not receded, but it's an issue of stochasticity. Sometimes it happens, sometimes it doesn't, like droughts, you never know. But I would say, based on my experience, that one or two events every year, it's very likely in these two channels. Now, whether it'll get to up to 6 or 10, I do not know. The record would show. Um, Fortunately, the city of La Paz has a lot of disasters. So they have an agency in charge of disasters. And that agency, uh, they pumped a lot of money into that agency. They have a lot of resources, and they've actually been able, over the last couple of 3 years, been able to document with videos, which now everybody's doing it, of course, uh, the production, the development, and the actual passage of these waves through the channels. I haven't seen them in operation, but I know that they're capable of actually recording and registering the passage of the wave. Okay, so with that, then I'm going to head directly into this channel, and you're going to find this paper is a review. In other words, it would repeat quite a few things that I already said. We've been talking about this for 2 weeks already. This is the end of the second week. So there's a lot of things, which is good. It's always good to review stuff because if it's not new, then it's easier to digest. Okay, so I go in here into the abstract. The theoretical foundations and relevant experience with open channel flow instability are examined with the objective of controlling roll waves. The latter seem to recur with relative frequency in channelized river where the Vedernikoff number, remember, the river has to be channelized, made uniform, prismatic, in order for this to happen. In a channel that has not been channelized, roll waves do not happen for reasons that ought to be obvious. The friction goes up, the cross section helps. The cross section is not prismatic, and it helps to control the roll waves. Okay, we show that beta, our beta, the exponent of the discharge flow area rating, is of paramount importance in the control of roll waves. Several examples show conclusively the existence of a definite relation between beta and the Vedernikoff number. That is the cross-sectional shape as the cross-sectional shape departs from rectangular, beta decreases. And we know that. We know that for rectangular channels, the beta is 5/3. For triangular channels, beta is 4/3. And for the inherently stable channel, which is an idealization, the beta is equal to 1. When weight is equal to 1, you can never, for any number, for any root number, can have a roll wave. We already discussed that. We said that inherently stable channel is an idealization, is impractical. You don't want to do that because you'll never get a fruit number of infinity. The fruit numbers usually top at about 25 to 30. So we could reduce the size. We can, using the same concept, which we already have done, and we have a calculator for that. So I'm not going to dwell on that. So the methodology described here is applied to two channelized rivers. So since I was already out there, and Beatriz is an engineer, she's a civil engineer working at the time with the agency in charge of these things. So I was able to coordinate with her. We went to the field. I was there for 3 days in La Paz. We did some filming, I believe. Not quite sure. Yeah, I guess we did. Yeah, filming, pictures, and so forth. And I was able to come back with all the data. They gave me all the data that they had. They had quite a bit of data. So let's go into the intro in here. Into the intro, this is going to be a bit repetitious. You already have seen the Cornish famous roll wave picture dated 1907. So I'm not going to dwell on that. You also may have seen, maybe not, this newer picture of mine. This happened when I was in the year 2007 in southern Peru. I was invited by the university out there, and then they took me to the field because they wanted to show me an irrigation project that they had done. So since I love the field, I said, sure, the field gives me the opportunity to take pictures and increase the size of my website, right? Besides, I am with them and so forth. They're always giving me the data. Uh, so we went over there, and to my luck, and Professor Ponce always lucky. The moment I was there, we were in that particular site only about an hour. The moment I was there, for some reason, they were releasing some water in the two lateral channels. And sure enough, these channels are very steep, and therefore we have the roll waves. So I took the opportunity to take pictures of the roll waves, my own roll waves, the ones that I saw, that I documented in Puno, Peru. Of course, we have several other occasions for this, but this picture is the one I took. Also happened to me up in North County in the year 2005, and I may have already shown you those rollways were kind of laminar in the laminar regime, and I have shown you also the picture, or rather the video of the rollways, the laminar rollways that came down the hill from where I live, from just right outside of my home. So we have videos and we have pictures of these events, pulsating or rollways. Unusual and often fascinating phenomenon to be admired by those fortunate enough to observe it. However, sometimes it could be dangerous. If they're large, it could be dangerous. Now, Montuori said in his paper that he didn't think that the rollways could be large because he said that when the depth increases, the mechanics is such that it has a tendency to not to develop. However, we have seen these rollways in Bolivia in film. We know that they could overcome the depth of the size of the channel, for sure. And since these roll waves appear to recur quite a few times in Bolivia, then we got to look at the Bolivia experience because it's paramount for us to understand the mechanics and how we could eventually fix this. Okay, so we focus on a case study in La Paz Bolivia, where roll waves have been documented to recur with troubling frequency in certain channelized rivers. There's several channelized rivers. Two of them are the ones that have the problem. Locally, these often large roll waves are referred to as pulsating waves. La Paz is about 800,000 people, and the seat of the state of Bolivia, or rather the country of Bolivia, they call it the plurinational state out there. That's a name that they themselves have given over the years because they have a lot of communities out there, you could say. I don't want to talk about that, it's politics. But the point is that that's Bolivia. La Paz has features a peculiar geomorphological setting. I did talk about that. I can't tell it in words because you got to see the thing. It's a hole, and you can see the hole out there. I have a picture here. I took this picture. It is almost entirely built inside an immense gully. It's not really a hole. It's a gully. It's a geologically described gully, or geologically described in terms as a gully, with several steep gradient streams draining its eastern side. So the gully, you got to enter into the hole of the gully somewhere, and you enter through the eastern side. Actually, you can also enter to the other sides because, I mean, after all, you got to get out of the city, right? So they have very steep roads coming down those walls. And as you can see right there, that stuff that you see in the back is just construction. It's buildings. Um, you don't see a lot of color in there. You know why? I don't know if you guys have been out there, but I've been several times to La Paz. That downtown is where I'm taking a picture from more or less downtown. But in the back, there's not downtown. It's just the city itself, and there's a tendency for construction to be like that or to look like that in La Paz. That's just the way it is, right? So it's kind of an a little bit of an odd situation. Odd situation. I guess you could say, if you want to describe it, is a city that does not look nice. And I would say it depends on where you are. If you're downtown, it looks really nice. But if you move off from downtown, then it may not be too good looking in terms of, or I guess you could say nice looking, not good looking, but nice looking. So that's La Paz. Over the past 30 years, urban development has resulted in the channelization of several of the main tributaries, measuring line channels. As constructed, the drainage canals have modified the conveyance cross-section so that roll waves are now recurrent, where they did not exist prior to channelization. With the menace of global warming, it is expected the intensity and frequency of these events will increase with time. We don't know. We don't really know a lot about global warming. All we know is that the planet is warming up. And when the planet warms up, there's one thing that is going to happen. There's going to be more evaporation from the oceans. And that evaporation, a lot of it is going to go inland. And then it's going to precipitate because that is just the way nature put it together. As a matter of fact, it's been said that if the albedo of the Earth was as low, was not higher than the albedo of the ocean, then the water wouldn't move in, and all the land will be a desert. But it so happens that because the albedo of the land is higher than the ocean, the physics, the mechanics of the atmosphere is right there, that when the water evaporates from the ocean, it moves inland. And it creates the conditions for which we have precipitation, right? So that's the way it works. We showed two videos. We already seen the videos, so I don't think we need to dwell on that. So in this article, we'll review the historical background and examine relevant theory, experience, and possible solutions to control, attenuate, or manage these waves so that society may be assured that they will cause no harm to people or damage to property. As I think I already mentioned, I believe there have been one or two deaths in Bolivia directly caused by the rollways. Unsuspecting, maybe people that didn't know what they were doing, but at any rate, it has happened. Otherwise, you stay away from it, and you can always stay away from it. It's a constrained river, although some of it does come out. As you can see it right there, there's water coming out. So if you're out there very close to it, it could carry boulders. I mean, you could get really hurt. So historical background. I'm going to go rather quick on this because we already talked about it. We have mentioned Vedernikov, we can mention Kraya. We mentioned how Kraya wrote a paper Now I believe even earlier, dated a couple of 3 or 4 months earlier than Vederniko. But then he had to come to the United States to publish his second paper where he spelled it all out. And I could not read Vederniko's paper. It was intricate. It was a translation from Russian. It was in English, not in Russian. In Russian, I would not have read it. But I couldn't understand the whole thing. It was very intricate, very complex, the mathematics. But when I saw Kraya and I understood Kraya better, I realized what they had done. I realized what they had done because I had the background of the ISCAR. So then I put it all together. That was 1985, 1986, and then I put it all together and I published my paper in 1991, clarifying the whole mystery of the roll waves because it was a mystery up to that. It was such a mystery that Chow did not understand. If I may be allowed to say that, Professor Chow has been dead for 30 years, but Chow did not understand that. Chow just said, "Well, these are the equations," and he copied them, and he wasn't too sure about it. So he hit the Vederniko theory as the last section on chapter 8. And by titling it theoretical concepts, he was assured that most people weren't going to touch it. And that was correct. I have talked about that extensively. So for many years, it was hidden. Even to this year, it's hidden. The concept is still hidden to many engineers that don't read it. I can tell you stories about it, many stories, but I'm not going to. So Ponce presented a unified theoretical treatment. We already covered that ground. Analysis followed on earlier seminal work. It was seminal work by Ponce and Simons. I do believe that, which laid the foundation for the complete analysis of unsteady open channel flow across the dimensionless wave number spectrum. We identified the dimensional wave number, and then we created or we plotted on the dimensional wave number spectrum. That is our S-curve. We confirmed Kraya's findings, Vedernikov's number also. So the Vedernikov number. We identified three velocities: the velocity of Manning-Chezy, the relative celerity of kinematic waves, and the relative celerity of dynamic waves, which come directly out of our S-curve. And then we have the definition of hydraulic variables. We did this for the purpose of clarity. We want people to read this and to understand it on first reading or second reading. We don't want people to spend too much time on it because they'll drop it. That happens with many papers that are written in the journals. You give yourself some time in order to read the paper, maybe a couple hours. If you can't understand in a couple hours, you drop it. I know that because I do that too. Okay, so clarity is important for the propagation of knowledge. That's a fact. Okay, so since we are not restrained in here into what we write, we just make it clear. So definition of hydraulic variables is the purpose of clarity. In other words, it is for you. Okay, we all know these numbers. Therefore, there are only three characteristic velocities, and three characteristic velocities lead to only two independent numbers, and those numbers are the fruit and the Vedernikov. That's it. There is no other velocity in open channel flow. I looked for one. Maybe I could come up with another number. No, there is no other velocity. There's the Manning-Chezy, which is only one, is the steady flow velocity, and then the unsteady flow, the short waves and the long waves, and that's it. Okay, so fruit numbers are independent of each other. It's not like what Vedernikov said and Chow kind of emulated or actually copied, that the Vedernikov is a function of the fruit number. No way. They're totally independent concepts. It is only a function because Vedernikov chose to write it that way because he obviously didn't know the whole story. He was breaking ground, right? But they're not. Vedernikov is not a function of the fruit number. They're totally independent concepts by definition. But it just so happens, by the way they're written, that it looks like one is dependent on the other. It looks like, but it isn't. That is where we came up with clarity. So we have the beta, our beta factor over here. We already talked about that. Interestingly, the beta, if the beta is a function only of the Vedernikov and fruit, then that means that the exponent of the rating is a function of beta, which is a function of Vedernikov over fruit. That's fascinating because prior to this formula, prior to our formulation, the exponent of the rating is a mystery. You just go out here, you're out there and find it and plot it, and that's it. You come up with a power function, and that's a power function But now we have said that the exponent of the power function has a theoretical meaning, which is 1 plus v over f. The Froude number, the Vedenikov number. Okay. The roles of mass and energy are central to the analysis. It is well established that while kinematic waves transport mass, dynamic waves transport energy. Therefore, the occurrence of roll waves is seen to be related to the unsteady transfer of mass, overcoming the unsteady transfer of energy. In this light, roll waves are a curious physical manifestation of the preponderance of mass transport over energy transport in unsteady open channel flow. Effect of the cross-sectional shape, the Vedenikov number, and the definition of the Vedenikov number in terms of the Froude number. But this is an algebraic expression because, like I said, by definition, they're independent. And then we have come up with this Froude number for neutral stability, which is obviously coming out of the algebra, which is 1 over beta minus 1. So we need to examine the true nature of beta. As you guys really know, beta is the excess, the celerity equal beta u. That means beta is the celerity over u. In other words, the larger the beta above 1, the more the celerity. And since the celerity has a tendency to become nonlinear in time and space, it will try to overcome. It will produce the so-called roll waves because that's just the way it works. So beta has to be more than 1 for anything to happen. Now, the question here is beta a floor for beta equal to 1? And the answer is no. Because when you have a channel like a culvert that closes on itself like a culvert, a circular conduit, it can be shown that beta could get values of 0.9 or 0.95. And that, by the way, is written in Chow's book. Interesting. He wasn't calling it beta, but he is talking about that, the exponent of the rating being less than 1. So it is not correct to say that beta varies from 1 to 1.4 to 5 thirds. There are situations governed by the cross-section where the beta could be, as an exception, less than 1. And the exception is for culverts, for closed channels that are operated under, they're not operated under pressure. They're operating as a channel, like a culvert, exactly like a culvert. That's exactly what it is. So the beta is a function of boundary friction and cross-sectional shape. That is what Vedenikov said from the beginning. And that's where the issue gets a little bit confusing, because when you enter laminar flow in there's an equation, remember, and it gets really confusing. It took us a lot of time to unravel all this stuff, Porras and I, when we did this work in 1995. And we also have the issue of laminar and mixed laminar and turbulent, because as we know very well from our practice of hydrology, overland flow has a tendency to be laminar and channel flow turbulent. But in the middle, you can have the Horton flow with the beta is equal to 2 in between 3 and 1.5. So that is mixed laminar turbulent. So it does complicate the issue a little bit. In practice, the issue, what is the value of beta? And like I said, I think I mentioned this earlier many times, that Horton was doing the calculation of beta. I think he called it M, but it's the same thing. In the watershed, since he was repeatedly coming up with 2, and he was wondering what the heck's going on. I mean, I'm supposed to get 3 in here, and I'm only getting 2. And then he finally figured out that it was a mix. It was a mix. Okay. Horton was considered to be the father of American hydrology, by the way. He wrote a series of seminal papers in the 1930s, which all of you that are interested in the historical aspects of hydrology, particularly in the US, should read. Get a hold of the Horton papers and read them. What's the name? Duke actually extensively talked about Horton in his book, which we have read, by the way. You may not remember, but we have read. We actually didn't spend a whole lot of time covering Duke, by the way. So it's probably okay or likely that you don't remember everything I said. I may have said it quickly. Another thing, I had to do this treatment for my book when I wrote my book. So I read extensively on the Duke theory, linear theory, and so forth, and I was able to put Horton in there. As a matter of fact, in my book, in chapter 4 of my book, we're coming up with a few statements that are there for the first time. For the first time. One of them is the fact that the kinematic time to equilibrium is only half of the diffusion time to equilibrium. That had not been mentioned before. And I believe I have explicitly talked about this. So we get the stable, which is a famous table. It's in my book, where beta varies from 3 for laminar flow to 1 for inherently stable. And it comes down to 8/3, 21/8, and so on and so forth. And it produces on the right side the fruit neutral stability fruit numbers in the various conditions. The first one's laminar, the Izzard flow. Then the other is Horton's flow over here. And then turbulent Manning, which is not Horton, turbulent Manning, turbulent Chesi, Manning and Chesi, right? I think I've already mentioned to you that Manning is a practical equation, while Chesi is the correct theoretical equation. I say that, I stress that. I believe Chesi is correct. Manning is not correct. But yet, 99% of the engineers out there use Manning because somehow, luckily or out of luck, Manning got the luck over 130 years ago, and people started using Manning. And they have a tendency not to use Chesi. And what they're saying is, well, Chesi was varying with the stage while Manning doesn't vary. That's not correct. All these values vary with the stage. That's obvious. But, be it as it may, that's the history of what actually happened in terms of the recognition of these two gentlemen. Chesi is theory, Manning is practice. Chesi is correct, Manning is incorrect. Yet Manning is used by 99% of the engineers. One of the reasons, well, not one of the reasons, but one could explain or justify this in terms of the fact that the Manning is only one value, while the Chesi is two. Chesi depends on the units. That's not true either. Chesi has two values outright. Chesi says for metric, this number, and for US customary, that number. While Manning says this is the Manning equation, but if you use metric, the coefficient is 1, and if you use US customary, the coefficient is 1.49, which all of you know, by the way. So it's a different way of looking at it, but it's the same thing. Okay, so now we move in here to the yearly stable channel, which I've already defined. I talked extensively about it. This is an idealization. We would like to strive towards the yearly stable. We don't want to get there. It's impractical. I already told you that. However, we, with Marcela Diaz 5 years ago, developed the concept of the stable channel, which was not inherently stable, just a stable channel, by virtue of doing a numerical calculation where we can design a channel that looks like it opens up, but it does not open up a whole lot, therefore not occupying a whole lot of real estate. And that's a better solution. It's a better solution. Okay, so we have these equations over here. And now this is an important table, by the way. Values of beta for selected values. Values of beta for selected values of fruit neutral stability. So if we want fruit neutral stability of 2.5, the beta has to be 1.4. Okay. If we want 3, if we want to assure a little bit more safety, because neutral stability 3 gives a little more safety, because the chances of the flow getting up to 3 is not quite a whole lot. Let alone 4, 5, or 6. By the time you get to 10, it's almost impossible, right? But the beta has to come down to 1.1. If you go to 25, 1.04. If you go to infinity, it has to be 1. We don't want to get to infinity. We could rather leave it at 10 or 15 or 20. Now, here's the issue of design. If you want to do the design, you could say, okay, I'm going to set 10. So let me get a beta 1.1. And 10 is already extremely high, by the way. The BioRec in their lab in Denver documented the occurrence of root numbers and basically said it doesn't get above 20. I believe they have a chart that loosely goes up to 25. And that number can be calculated, by the way. We have proven extensively that it doesn't get up more than 20. So the Bureau is correct. They did correct. They did it experimentally, but we have done it theoretically. So there's no reason to go. 10 is already high, in my opinion. I have not seen a flow greater than 10. Usually, if flows go high, they go 4, 5, 6, but they don't get to 10. So it's good. So all we need to do is a beta 1.1, and we would have done it for 10. Or if you want to go a little bit more risky, you can go to 5 is 1.2. But definitely not 1.67, which is a rectangular channel. It's 5/3, okay? Or 1.5, which is the Chesi. So you don't want to be there because 1.5 is already putting you in the category of 2 in here. And 2 could be achieved. One, if 1% is, if 1% slope is fruit number equal 1, roughly, then about 2% slope is 1.5. By the time you get to 3% slope, you're already fruit number equal 2. As a matter of fact, the channels in Bolivia are 5.6%, and they already have Vedernikovs of 1.5 or 2, Vedernikov, which is fruit equal 4. We will show that calculation. Okay, so let move on. I got 10 more minutes. We're gonna get done in here. Shallow wave propagation. I don't need to cover this. You already know it. Here is well summarized, but you already know this stuff. So I really don't need to get in here too much. We have this graph, our S-curve graph. This is for the attenuation, and this is for the attenuation of the fruit numbers greater than 2. Actually, amplification is negative attenuation. The first one is minus delta. It's attenuation. And the second one is plus delta. This is amplification. And these are the numbers that came out. This is very revealing because it already said that the fruit numbers for the high fruit numbers greater than 2, say 3, 4, 5, the wave numbers towards the middle left of the climatic spectrum are the ones that are going to be amplifying. So if you're out here somewhere, no, you're not amplifying. It's too low. Look at this. This is logarithmic. So, I mean, it's 10 times. From here to here is 10 times. From here. So, 0, no, 1, 10, 100, 1,000. Yeah, so that's 10,000, 10,000, I'm sorry, not 10,000, 1,000-fold effect on whether the flow is going to amplify or not, from the extremes on the left and right to the middle. So that does tell us. Experimental verification, sure enough, we already covered this ground. I believe it was last Tuesday. Meissner came up and he wanted to do a study, and I said, I've got this report which you can read, and then you can help me out. And we did. We wrote this paper, and we showed that the Brock data plotted close to the point to the peak. We were not disappointed that it didn't plot at the peak. Why? Because we don't know. Brock could have we could have misinterpreted a little bit, or Brock could have been doing the wrong measurements, or whatever. But the point is that we were close enough. Nothing's perfect in this world. Close enough. I mean, if it was gonna deviate, it would have been right over here. And then if my points had been down over here, I would have said I messed up or Brock messed up. Somebody messed up. It doesn't match, but it does match. I think you will agree with me that it does match. Wave diffusion versus wave amplification. Okay. Whether a wave diffuses or amplifies will depend on the effect of boundary friction and the effect of cross-sectional shape. So it is boundary friction and cross-sectional shape together that determine whether the wave will diffuse and amplify. However, that is, both of these values or both of these physical parameters or conditions are expressed in the celerity of the wave together. So it's better for us to look at the celerity of the wave than independently try, as Bedenikov tried to do, to separate the friction from the cross-section. The strength of the attenuation will depend on the fruit number and the dimensionless wave number. Lower fruit numbers undergoing markedly greater attenuation. Wave attenuation peaks near the mid-range and right of mid-range of dimensionless wave numbers. I've already shown you this stuff. In conclusion, managing beta at the design stage is a sure way to control flow amplification and thus avert flow instability. A hydraulically wide channel features 5/3 for Manning friction and 3/2 for Chesi. Therefore, it is preeminently not conducive to wave diffusion. In other words, a hydraulically wide channel will not diffuse. Moreover, a rectangular channel cross-section is the closest to hydraulically wide. In other words, we obviously don't have a asymptotic hydraulically wide, but if the channel is rectangular enough, the betas will be on the order of 1.6, which is close enough to 1.67. 1.67 is the limit. You cannot go above 5/3 Manning and 1.5 Chesney. If we're in doubt as to whether it's Manning or Chesney, and many people are, if Chesney is 1.5, you already have 1.6. So you're already above Chesney, not quite Manning, but above Chesney. So you're in this gray area where nobody really knows which one of these two formulas applies, okay? Moreover, a rectangular channel cross-section is as closest to hydraulically wide. Therefore, rectangular channel cross-section is also not conducive to wave diffusion. Values of 4/3 or 5/2 are more conducive to wave diffusion since they raise the value of the Froude number above 3 or 4. If Froude numbers above 3 or 4, you gotta have a very steep channel in there. Even if the Bolivia channels didn't get there, I don't think we'll calculate that. The Bolivia channels are already very steep. So I submit that we're here at the practical ceiling out there. Practical ceiling. We probably wouldn't get to 5. If we wanted to get to 5, we were going to purposely or forcefully try to get to 5, and that in practice is not going to happen. Calculation of beta. Okay, so we calculate beta. We have an online script to calculate beta. I hadn't done this. I went to Bolivia to gather facts, gather data, gather pictures, gather videos, and so forth. And then I came back and I realized, I studied, I looked at it, and I said, it's a simple matter. All we need to do is generate a rating in a prismatic channel, which we could do. And we do that all the time. Generate a rating and fit a power function to the rating, and we're going to get the beta. And sure we did. And that worked beautifully, by the way. And we did it all in the calculator. So we have a calculator. This calculator, actually, the first thing it does is it takes a look at the channel that you have told it to design, generate a rating, and then fit a curve to the rating. In other words, get the alpha and the beta. So we have in here. So the input, online channel 15B, is bottom width, the bottom width of the channel over here, the flow depth, the side slope 1, side slope 2. We did both. We did them differently because we wanted to provide general cases. Sometimes this does happen. I have experience with this. One day we designed a trapezoidal channel, and somebody out there in the world used it, and they said, well, you know, Professor Ponce, I would like to have a channel that, I would like to have a difference Z1 from Z2. So I said, that should be easy. But interestingly, I tell you a story about this. That I did the equation. I figured, oh, well, I'm going to sit down and I did the equation, but I made a mistake. Nobody's perfect. A month later, we got a call from a friend of mine in Bolivia, professor over at Cochabamba, University of Cochabamba. He said, Ponce, Dr. Ponce, the calculator is great, but you made a mistake. I said, really? How fascinating. I respected his opinion, of course. He's a professor. He's a good guy. He's from Europe. He just emigrated to Bolivia and stayed there. Got married there, and he's out there. Don't remember his name right now. But he did say, yes, I actually reproduce your algorithm or not. I did it in Excel because everybody uses Excel. And it doesn't come out. And I checked it, and I know you're wrong and I'm right. I said, okay, fine. I went back, and sure enough, I had an omission. So I fixed it. I thank my friend profusely. Is one or several, maybe 2 or 3 occasions where people out there in the world have actually come back and corrected me on my calculators, which is good, by the way. That's the way we do it. But you had to have somebody that really knows what they're doing in order to correct a calculator that has been put out, because they got to start from the beginning. They don't have a ruler. They have to come up with their own ruler. And then they say, oh, well, the answers are different, so somebody must be wrong here. Okay, so we have input data in here. I urge you to examine this, and you're gonna have to run it before you actually learn it. Okay, so we gotta, okay, there it is, there it is. There it is. We have in here stream, select units. The discharge here is not given. The discharge is by trial and error. So you give the bottom width and the flow depth, and then you calculate the discharge. So if you're given the discharge, then you back calculate the depth by giving it the discharge. In other words, you give it the depth in order to calculate the discharge. If the discharge is not the one you want, then you got to change the depth because the width is already set. It's the depth that is being changed. So for instance, in here, with 5.8 and 1.066, we get a discharge of 50, which is what we wanted to get in the first place. So the discharge is obtained by trial and error. Flow velocity, Froude number, beta exponent, 1.6. So this channel is unstable. It is unstable because the technical is 1.5. The beta is 1.6. I already told you, between 1.5 and 1.67 is in this gray area where people don't really know if it's really Chesney or if it's really Manning. Actually, it's in between. And by definition, not because of physics, but by the way we define this, okay? And we use Manning's for the simple reason that if we wanted to use Chesney, nobody would use it, right? I mean, we got to be practical about this. So this is the calculator. And we explain in here the results. We explain the results and so forth. The nature of beta. The value of beta is smaller not only for triangular channels, but also for narrow channels. I'm going to start making a little faster view in here. So we have a test channels in here. We tested at rectangular, triangular, narrow, and deep. We believe that narrow and deep is the solution for this, by the way. The narrow and deep. But most people don't want to make too deep a channel, so they got to calculate it. I want it deep, but not too deep because I don't want to build that deep, right? But a deep and narrow channel will force beta to drop below 1.1. And therefore, it would, perhaps not 1.1, but it will drop. And therefore, it will be conducive to stability. Okay? So that's basically the way it works. Conclusions. Mechanical control. We invented this stuff. We really invented this stuff. The technical criterion is seen to be a necessary condition, but it may not be sufficient. There is a preferential scale of dimensionless wave numbers. Whether a roll wave event will occur may also depend on the upstream boundary. Remember, I told you there's stochasticity in here. Sometimes it happens and sometimes it doesn't. There's a randomness or stochasticity about the occurrence of a roll wave event, which precludes it from happening too frequently or otherwise at regularly timed intervals. So we came up with what we call a diffuser. Since I already mentioned to you that the deep channel would produce diffusion, then instead of making one channel rectangular, we would make 2, 4, 6, 8, 10 channels which are deep. Each one of them are deep. And we do believe that will diffuse at the entrance. If it's placed at the entrance, it will diffuse all the bad waves that want to become amplified waves downstream. They will be diffused completely. So this is what we call a diffuser. By the way, a diffuser is not a new concept because it is used, for instance, in overfalls. They have diffusers at the end because they want to help the diffusion. The diffusion is natural, but it's slow or maybe slow. So we want to help the diffusion, particularly when you throw stuff in the ocean. All those structures have diffusers of some kind. And of course, diffusers of mass could be diffusers of mass and momentum or energy. In this case, we have diffusion of momentum, not of mass. We're not diffusing the water, we're diffusing the momentum, the unsteadiness, which is the momentum. Unsteadiness is momentum, right? So we have this. But suffice it to say at this point that the structure has, to my knowledge, never been built because it's relatively new. I have not heard anybody that calls me and says, hey, we like your idea, we're going to build this thing. It hasn't happened yet, but it will. It will in the future. In order to do that, I was in Tamaulipas. We did work in Mexico several years. Not now, but for 5 years or 6 years, I was working in Tamaulipas, Tampico, Tamaulipas, Mexico. We had a contact at the university over there. And one day I ran into this channel. And I was really surprised. So really a deep channel. Why would it be there? And the reason is they didn't want to make it too big, perhaps because they didn't want, they had to put it there, and they didn't want people falling into the channel. it would be hard for anybody to fall into this channel. First of all, you can't fit in there. You may hurt yourself, but you're not going to get killed or swallowed, right? You can't fit in there. So they made a deep channel. That may be the purpose. I didn't talk to the designers, but they made a deep channel. And I am positive that because of the cross section, this channel will never overflow. If it does have the rollways are coming in, it would not overflow. It would just simply attenuate all the rollways because of the issue of its cross section. The beta over here must be on the order of 1.2. And I already told you anything less than 1.3 is conducive to attenuation. So finally, case study La Paz, I'm going to skip this, okay? And I may come back later, or else I'm going to have you look at it carefully on your own. But we have a case study over here, because I want to get into the other paper. I have to. We have the Achumani River, the Wainayawira River, and the pictures of both rivers, the Achumani River like that. Look at what they did in there. The rectangular channels completely. Well, it's interesting that at least the Wainayawira has steps in there because they figure they could control the rollways with the steps, but they don't. The steps don't control the rollways because we know that the steps are there and the rollways are still there. Okay, so please review this stuff. It's kind of detailed, but we got the betas in here, the Achumani. Look at the betas that we calculated on the Achumani. Of course, this is going to fail. 1.6, I already told you, anything about 1.4 is dangerous. 1.6, 1.6, 1.6, right there. Vedernicus, 1.5, 1.5. It is supposed to develop the instabilities. So finally, the conclusions, which I already said, that theoretical foundations are examined with the objective of controlling roll waves. It's shown the shortage of beta at the design stage before you do it. You got to hire the right people, hydraulics people that will do this sort of thing. It's not enough to design just a channel the way we used to do it, like that way with Chow would tell you to do it. Chow, of course, could not and would not cover this ground because he didn't know at the time. He barely knew about Vedernikov, let alone how to design control in a channel, design control of rollways in a channel. But this stuff in here is relatively new. Methodology is applied to two channelized rivers in La Paz, where pulsating waves have been shown to recur with increasing frequency, etc., etc. Okay, so field data was provided by the municipal secretary of integral management of risk. That's fascinating. Huge building that they have out there. They have all kinds of risks out there. Oh boy, I don't want to. When I was there, they had a slide in about a whole bunch of houses. I don't know how many, 30 houses fell to the ground. And one building totally just was obliterated by some slide. And why and how these slides occur? Because they have a lot of steep, it's a gully. And the people have actually built at the bottom and then they started growing into the sides of the gully. And as you can see the picture, if you have seen the picture, it's already covered. So there's a lot of houses out there. They're right there in the middle of where, if it rains a lot, it is going to slide heavily, propelled by the weight of the buildings and so forth. And there's buildings out there, so it's a risk. I wouldn't do it, but I mean, I'm not there, right? So, and I know that every once in a while they have slides. It depends on if the winter is bad, they have a lot of rain, and the rain seeps into the ground, and then it kind of lubricates the slopes, and then you have the failure. So that's why they have these people that are in charge of risks. Although I don't know how good a job they're doing, to be honest with you. I'm not going to comment on that. But let me just go back in here, and I'm going to be talking about the next paper. Now, this next paper originated in last year, in February of last year, because I had a collaborator from Brazil. There's a professor from one of the universities in Brazil, Instituto Federal de São Paulo, Campus Caraguatatuba, São Paulo. They have the University Federal de São Paulo. In other words, the state of São Paulo has got a whole bunch of, there's a lot of people out there, a lot of money, resources, and they have similar to California State University, by the way. similar to it. And then they have a whole bunch of campuses because a big state, big resources. The lady teaches over there, and she kind of exactly how I got to know her, I don't remember. But she called me and she says, I'd like to come and visit for 4 months sabbatical. I said, fine. So she came. Unfortunately for her and for everybody else, we were hit by the pandemic in the middle of her stay. So she had to leave. She was here only for 3 months. She was supposed to stay for 4 months. She had to leave because you remember March of the year 2020 was not very auspicious. That was the beginning of the pandemic here in the States. So she left, but we continued to communicate. We wrote this paper prior to she leaving. It's dated May, but we wrote it in February and March. So let's take a look. The reading of this paper and the understanding of this paper is going to help you do your homework. Because I built a homework around this situation. The design of a stable channel to be hydraulically stable is governed by the well-known Vedernikoff criterion. But the channel stability depends on the shape of the cross-section, whether it is trapezoidal, rectangular, or triangular. We know trapezoidal is no good. I'm sorry. No, take that back. Rectangular is no good. Triangular is better. Trapezoidal in the middle. Because if rectangular has 5/3 and triangular has 4/3, trapezoidal is in the middle. Because trapezoidal is a combination of rectangular and triangular, right? So we find out from this practice that the channel is going to have to be trapezoidal because building a triangular channel, a large triangular channel, is difficult. I don't believe it has been done. So we can do it trapezoidal, but we can do it trapezoidal in such a way that would look more or behave more like triangular than rectangular, because it would be kind of in the middle, more toward one side than the other, right? And that's exactly what we're doing in here. That's exactly what we're doing in here. In this article, we use the calculator 15b to calculate the beta and the corresponding Vedernikoff number. And the idea is to try several cross sections that are of trapezoidal shape by varying the width and the slope of the side in order to make the Vedernikoff drop down, and it will. And when the Vedernikoff drops down, the beta drops down. So basically, the Vedernikoff is a specification. Specify Vedernikoff less than 1. But the way to get there is to bringing down the beta. The beta has to come down before the Vedernikoff will go less than 1. And we do that by trial and error. You can run the calculator 100 times if you wish to do so, because it's so easy. It runs in less than half a second. Not even, less than a fraction of a second. So let's take a look in here. This is sometimes often repetitious, but it's fine. Repetition is not bad. Design of a line channel to be hydraulically wide is governed by the well-known Vedernikoff criterion. Here we use an online calculator. Theory, right? We go back to the Cornish picture, which I love, by the way. I think it's a great picture. 1900, and the date is even better. 1907, that's extremely early. 1907 is, I mean, we don't have too many references in hydraulic engineering that go prior to 1907. So that is really tremendous. Tremendous. As a matter of fact, Cornish was a geographer. He was not a hydraulic engineer. He somehow landed, or this picture landed on his feet, or I don't know how he acquired it, but he did write a paper on this. And the paper, by the way, has been published for you to read. It's right there. Royal Geographical Society, the Cornish paper. So if you're interested in the history of this whole thing, or the history of what Cornish did, you can go back and read it on our site. We specialize in doing that, by the way. We specialize in providing web tools for people. I could have very readily just hidden Cornish from you, but I'm not doing that. Our interest is to get people to learn this stuff. And the faster you learn it, the better. And you're gonna learn it when we provide ways for you to access the information. And as you know now from our and your experience with Google, it's a tremendous success. The web is a tremendous success from that standpoint. So we have the relationship, we already covered this ground, relationship between beta and V over F, it's already covered this ground. Hydraulically wide, the betas and the Froude number for neutral stability, the design of the inherently stable channel, the online calculator, okay? A line calculator calculates the value of beta, exponent of the rating, corresponding to rectangular, trapezoidal, or triangular channel. Input data is the following. Okay, so you're going to now set up to run this program. You're going to have to determine the bottom width. First of all, you know the discharge. The discharge has to be given to you. Your design, any channel, any design of any channel would need a discharge. And the discharge comes from the hydrology. People have asked me when I was used to teach, what's the difference between hydrology and hydraulics? And I said it's fairly simple. The hydrology will determine the Q's, and the hydraulics will determine the Y's, the stages, the pressures, to design the structure. Hydraulics doesn't get involved in the actual, hydrology does not get involved in the actual design. Hydrology is prep. You're prepping, you're preparing. So you're figuring out what the Q is, and the Q comes from the hydrology from the rainfall. So hydrology basically is converting rain to Q. In hydraulics, Q to Y, or pressure. Y and then pressure. So that's a division. But there are some cases where, particularly like flood routing, which are in the middle of it, you can't say flood routing is one or the other. Interesting. So that's where I leave that subject. I'm going to go back in here. So we have the bottom width, the flood depth, the flow depth, I'm sorry, the side slope 1, side slope 2, Manning's and then bottom slope. So you feed those in and you're trying to guess the depth because the width is by specification. So you're trying to guess the flow depth with the other given values that will get you to the Q that you want. It's a trial and error, but it's very easy, very straightforward. Output is the following. Intermediate values are wetted perimeter, top width, flow area, and they're referenced for you. They're printed out for you because you got to analyze the whole thing. Hydraulic radius, hydraulic depth. And here is the issue. The hydraulic depth is the crucial value in here. Why? Because the Froude number, which is directly tied to the Vedernikov number, is a function of the hydraulic depth, not of the depth, but of the hydraulic depth. So since the hydraulic depth depends on the area and the top width, then it varies with the width and the Z values. So that's the crux of this whole thing. The key to the understanding this is that you're going to be dealing with the hydraulic depth, not with the depth. Your depth in here, your flow depth Y has nothing to do with it. What matters is what are the C's and the B's for us to get to the hydraulic depth, because it is the hydraulic depth of with which we are going to calculate the Vedernikov. Okay, so we have the discharge, the flow velocity, definition, Froude number, definition. Note that the Froude number is defined in terms of the hydraulic depth. In many references, the Froude number is defined in terms of the depth, not of the hydraulic depth, but that's wrong. If you want to do a precise calculation, you would have to use capital case D, not Y. And this is where a lot of people make mistakes when they do modeling. They say, oh, the Froude number, Y. Well, no, the Froude number is not Y, it's D. And if they make that mistake, then they're making a 1 or 2% mistake, which of course in engineering is not that big a deal. Engineering does not count on 1 or 2%. But if you're doing modeling, which is not engineering, then you will pay a price. Modeling has to be correct and perfect. So we always use the hydraulic depth rather than the depth itself, as it's proven in here, by the way. If you replace in there the D, capital D with a Y, you'll never get anywhere. It just won't work. Believe me, we examined this, okay? Neutrally stable Froude number, because the Froude number is tied, like I said, I repeat to reiterate, to the hydraulic depth, not to the hydraulics, not to the depth by itself. So we calculate the Vedernikov number, results obtained by trial and error procedure, and the trial and error procedure is described here. The unstable channel. A hypothetical example is presented here. Assume a channel or rectangular cross-section of width 6b. Actually, the Bolivia channels, I think, is 5.6. But we are not really zeroing on the Bolivia channels. We want to use the Bolivia channels as a reference for what we're going to be doing. The bottom slope 0.06, theirs is 5.6, something on that order. Approximately simulate the conditions of the Huayna, Hiawira, and Achumani channelized rivers of La Paz. Okay, so we come in here, 2 pictures, okay, and then we have our calculation. And like I said, this is a trial and error procedure. You're going to give yourself various bottom widths and various depths. in order to match the discharge. In this case, we have specified 100 cubic meters per second for this particular example. So that's what we need to, and you can see we shoot for that and we get it. With what depth? With a flow width of 6, the side slope of 0, that's rectangular, and the flow depth of 1.638 meters. We go all the way to the millimeters, by the way, in the calculation. We had to go. Stop at millimeters over here. And then we get the right answer. The Verdenico is 1.48. Therefore, this channel is unstable. So this kind of emulates the situation, the local, actual situation in La Paz. So now we're going to the testing program. The objective of the testing program is to determine the hydraulic conditions in a series of alternate channel sections. So what we need to do in here is to vary the width between 1 and 5. Why 1 and 5? Because the bottom width is 6. We don't want to make it 6. That would increase the discharge too much. We can start with 5, see what happens, and then 4 and 3, all the way to 1. We don't want to make it 0 because it's triangular. So 5, 4, 3, 2, 1. So we have bottom width 5, 4, 3, 2, 1 over here. Okay? And then we're going to have 3 Z's. We're gonna get a Z 0.25 that is 1 horizontal and 4 vertical. We're gonna get another Z 1/2, 1 horizontal, 1 vertical, and then 1 which is 2. No, I am sorry, I take that back. 0.25, 0.5, and 1, right? 0.20, so 3 Z's. 3 C's, 5 widths, and as many depths are required in order to run the discharge of 100. So this would require at least 15 runs, right? It's five widths and 3 slopes. But no, in reality, I did 30, 40, 50, more, very quickly, easily, by the way, very easy. 1 hour and you'll get done with those whole thing. It's not a whole lot when you have a calculator. If you don't have a calculator, then it'll take longer. I remember I told you that when Arisa did his thesis in the year 2017 with me, he did it in 4 months. Well, you should have seen how fast he worked. I gave him about 5 or 6 calculators. And at the end, I mean, he thought it for a couple months, and then at the end, he just produced the whole thing in 2 weeks. Thousands of runs that he did with the calculators. That's the way to do it. Okay? So he was very proficient in doing that, and he finished, and everything was correct with the case of Arisa. Very smart guy. So finally, we conclude in here, as you notice in here, I'm going to get a little early, which is good, that over here with the Z 0.25, okay, the depth goes up, and therefore the Veternikovs are coming down. The Veternikovs are coming down, and we get to 0.55, which is a very good Veternikov. That means it guarantees that there's not going to be any roll waves out there. Even 0.82 would be good. Anything below 1, right? So for in this case, for this slope, which is 0.25, for the width 2, we get the depth over here, okay, 2.6. For the width 1, we get greater depth, and then, okay, so how does this work? We looked at this very carefully. When you narrow the width, you increase the depth. And when you increase the depth, you decrease the beta. And when you decrease the beta, you decrease the Veternikov. So the idea is to do all these calculations so that you will decrease the Veternikov below 1. I mean, you could, if you wanted to, get to, this is 0.55, this is 0.81, and this is 1.05. That means that I could actually design this channel with Z.5. I don't need to get to 0.25 because 0.25 is getting me to 0.55, which is a whole lot. If I only get it below 1, which is 0.81, I'm fine. So the second calculation is good enough. The third one is no good because the third one is giving you the lowest Veternikov, 1.05, which is unstable. So as you can see, this gives you a complete view of exactly what's going on in the channel. Of course, all this is contingent upon the fact that your Mannings is correctly estimated. If your Manning is off, then you're off too, okay? The Manning is crucial But we believe that we can indeed, based on the work that people are doing, have done, based on the reference and so forth, that we can get a good estimate for Manning. I believe the Manning in here, because this is the Manning that we use is 0.025, which is not too high, not too low. It's not concrete, and it is not natural. Concrete is 0.015, and natural is 0.05. So 0.025 is a smooth channel, but it's still bricks. Okay, so we finally get over here, and then we come up with the conclusions, right? Fruit number is a function of depth. It is noted ostensibly, or I guess you could say not ostensibly, it is noted markedly that the fruit number is a function of the hydraulic depth and not of the flow depth. The examination leads to the following conclusions. The smaller the value of Z, the larger the value of D, and therefore the smaller the value of F. Value of beta decreases sharply as the bottom width decreases from 5 to 1, and slightly as the slope decreases from 1 to 0.025. Within the tested range, the lower the value of Z, the faster the Vedernikoff number falls below 1. Now, at the beginning, we didn't know this because experiments give an analyst like myself and you a way to think about these things and look at the theory and find out if it does make sense. If it doesn't make sense, either made a mistake or you don't know what you're talking, right? But in this case, it made sense because it's related to the D, the capital D. And wherever the capital D was larger, then the Vedernikoff was coming down. And that is correct. Because the Vedernikoff, whether we like it or not, is tied to the fruit number, even though they're independent. They only accidentally look like they're dependent, but they're independent. So finally, our conclusions. The results of this study show that as the bottom width P decreases within the tested range, with side slope greater than 0, it has to be rectangular, non-rectangular, trapezoidal. The values of beta and V decrease accordingly. The reduction in the Vedernikoff number depends on the value of side slope, the reduction being faster when Z is smaller within the tested range. In other words, the smaller the side slope, the faster the Vedernikoff number. This is kind of counterintuitive, but it is correct. Because if you go to side slope 0, then the whole thing reverts back to the way it is. So, to the way it was, unstable. So there is somewhere in here a minimum and a maximum, which we haven't looked into, by the way. For this example, this is correct. But we know that we need to look at the effect of the depth. Because what we're doing here is manipulating the side so that the depth would increase so that the Vedernikoff can come down. But how far can we go manipulating that? That is the issue that is still in the research stage, and I didn't touch it because I promised Licky, our colleague in Brazil, that she would do the work. She wants to do the work. They want to identify research projects, to do the work, publish it, stuff that she could publish. So she is still hoping that she can do the work. She's been busy. She went back, and it's been a year and a half, and the work hasn't been done yet. So I don't know what's going to happen in the future, but either Leaky does it or I do it. But the chance of me doing it is difficult because I don't like to do things anymore by myself. Okay, I did suggest that this project be done by one of you guys, but none of you guys took it. I guess you guys may have gotten scared because I did say that that was research, meaning research that nobody had ever done. But it's still there. All we need to do is run this calculator again and write a paper looking at the betas on the order of 1.1, because right now we didn't get there. Where are the betas here? The betas. 1.5, 1.38 for this case. 1.5, 1.35. And for this other case, 1.5, 1. So we got to 1.32. Our lowest beta was 1.32. We want to get to 1.2, 1.1, and we can, based on the experience that we have. I have experience with this, by the way. It's not the first time we do this. I can show you papers which I have already discussed, where when the beta comes down to 1.04, 1.05, the whole thing diffuses like nuts. It's crazy. The beta is controlling the diffusion. Okay? So that's basically the end of this. It is concluded that the value of B that reduces the Vedernikoff depends on the value of Z. Line calculator is a useful tool for the analysis and design of line channels with the objective of promoting flow stability and avoiding roll waves. I'm not going to show you the channel, the video, because you already have seen it. So I'm 2 minutes short now from the end of our class, and I'm just going to leave it at that. And you should begin. I'm going to assign that. I think I already did assign. So I gave you 2 weeks because I know that it's kind of intricate. 2 weeks to produce that last homework, by the way. And then after that, there's no more homework because I want you to do your project. I don't want your project to interfere or the homework to interfere with your project. Okay, so we're done at this point. If there are any questions, of course, you can always reach me at any time. I always say half jokingly of the day or night, but I always check my 2 course emails. I check them frequently to get back to you. And experience shows that I have gotten back to you when you requested my attention. Okay, so with that, then I'm just going to cut it at this point. Thanks for listening. I'm going to stop the share, and I will see you when? Monday. Oh, by the way, next Monday, we're going to get into an entirely different subject. We're going to talk about numerical mathematics, the core, the essence of this whole thing. How come I left that almost to the end? No, it's not the end. It's the 12th week. It's fine. Okay? We're going to talk a lot of interesting things that are at the core of numerical mathematics. It's not even hydraulics. It's just numerical mathematics. But it applies to what we're saying because it's numerical. And this is computational, that is numerical hydraulics. Thank you very much. Bye-bye.